We'll walk you through part 2 of the week 5 doc. All right, so let me just get my doc up. Yet again, we're doing a fake experiment, but it's based off of a real experiment. So before I jump into like filling out our doc, I want to walk through this. There's a famous study from 2003 that compared how many callbacks applicants got for jobs, and that just means like you send off your resume and stuff, and then do they ever call you back? Based on whether the applicants' names were traditionally white, the names they used were Emily and Greg, or traditionally black, Lakeisha and Jamal. The study found that applicants with the white names were called back much more frequently than applicants with black names. Even at companies, they said that they value diversity. This is one example of the many layers of white privilege and anti-blackness that perpetuates our socioeconomic inequalities. We're going to dig into this a little bit. If we were in class, I wouldn't have introduced that at all. I just would have passed out these resumes. I screenshotted just the first parts of them into the doc so you can see what they would look like. And I wouldn't tell you this, but secretly, all the resumes would be the same, except some would have the name Emily Jones and some would have the name Lakeisha Jones. I would ask each person to decide whether or not they would call the candidate for an interview, and then we'd look at our data. As usual, I have to give you some fake data because we can't actually do this activity. So let's say that the results, our fake results are listed. So I said out of 15 that maybe 12 people would want to call Emily back. Out of 15, maybe 9 people would want to call Lakeisha back. Maybe this would be totally wrong. Maybe you guys would be like, nah, Lakeisha's it. We're going to call Lakeisha. I don't know. So this is made up. But this is a real experiment, and so I sort of based this result, our fake results, based off of what happened, like when the experiment was actually conducted. Okay, so question 1. Without performing any other calculations, do you think this is a significant difference in callback proportions? So we have 80% of people wanted to call Emily back, 60% of people, wanted to call Lakeisha back. So opinion question for number 1. You can answer how you wish. Do you think that's significant or not? All right, and now we're going to walk through question 2. Question 2 is a long one. Is there convincing evidence of a difference based on the name alone? So in question 1, it's just sort of like, all right, real quick, do you think this is a significant difference? Question 2, we're going to walk through something called the significance test, which will allow us to actually say, like, yes, this is a significant difference, or no, it's not. All right, so here we go. On yours, actually, we don't need to keep listing out our population and our sample. So I'm just going to delete those off your doc, and then we won't talk about them anymore. Because hopefully you're kind of clear on just what those mean. Okay, so crossing those off. Our parameter here is what we are really trying to find. So the parameter would be the true difference in callback proportions. And careful where your parameter is, it's in a different box, but just make sure you're putting it in the right spot. That's P1 minus P2, and I'm just going to say it's going to be Emily minus Lakeisha. There's no like one right way to do it. Emily minus Lakeisha, Lakeisha minus Emily. It's just we got to say it and be consistent with it. Okay, so our statistic, I'm just going to put that down here because I ran out of space up there, is based off of our sample. So P hat sub 1 minus P hat sub 2. This is based off of our fake data. So our callbacks for Emily minus our callbacks for Lakeisha gives us our statistic of 0.20. All right, for the hypotheses, our null hypothesis would be that like everything's fine here, nothing interesting is going on, the true proportions are the same. So I'm going to write that out as the proportion of callbacks for Emily minus the proportion of callbacks for Lakeisha is 0 because they're the same. Our alternative hypothesis is that they are not the same. I'm going to set this up as a not equal to 0. Based off of the experiment, I don't have the actual study open anymore. I'm just wondering if, I think their hypothesis would just be that there would be a difference based off of like the racial, like perceived racial identity of the applicant. Probably the people, when they were writing it, they were thinking that there would be some discrimination just based off of social stuff in our country. But the hypothesis most likely was just that there would be a difference between Emily and Lakeisha, even though their resumes are the same. So that's why it's going to be a not equal to 0. Okay, and our significance level is done. 5%. Alpha is 0.05. All right, so that's our state section. Oh, by the way, your check for understanding, if you want to scroll down to it real quick, you're going to have to walk through these steps, but without like all the fill in the blanks. So just, be on the lookout for that. All right, next up is plan. So the name of the procedure is the same as what I did in lesson 1, part 1. It's the 2-sample z-test for P1 minus P2. Checking our conditions. So let's see what we have. Random. Yes, the resumes, if we did this for real, were randomly passed out. Okay, for the 10% condition, we actually have no need to check because we're not sampling without replacement. You only need to check that if your experiment, you are doing sampling without replacement. And then for large counts, let's see. I need to use my combined p-hat for this. Whenever we're conducting this test of a difference in proportions, we have to get our combined p-hat. So let's go back and look at our data, which I didn't even put in here. Unfortunate. Okay, so I'm just going to write that out real quick. So callbacks for Emily, Lakeisha, sample size for Emily and Lakeisha. Okay, so it was 12 out of 15 and 9 out of 15. Okay, so our combined p-hat, basically we're going to be like smushing up Emily's data with Lakeisha's data. So total callbacks is 21 out of my total sample of 30. This gives us our combined p-hat. So that'll be 21 out of 30, which is 0.7. All right, so I'm going to go back over where? Over here. Okay, so I'm going to take for Emily, I'm going to take 15 and multiply it by 0.7 for my expected number of successes, and also by 0.3 for my expected failures. So that's going to give me 10.5 and 4.5. And then for Lakeisha, it's the same sample size. I'm still going to write it out though, just to make sure that it's clear. And you can see here, similarly to the last one we did, the large counts condition is not met. We're looking for all of these numbers to be greater than or equal to 10. So for the number of successes for both applicants, it works, but for the number of failures, it doesn't. So all that this means though is that we can proceed with caution. Okay, next section, do. First of all, we have to find, okay, what is our mean and our standard deviation? Then we can use that to help us calculate all this other stuff. This stuff we haven't seen before, so like, you're just going to do it with me. Like, don't feel bad. Like, I want you to just follow along and try to fill this stuff out as we go. In the check for understanding, well, we'll do notes first. And then in the check for understanding, you'll get a chance to try this out on your own a little bit more. Okay, so to find our mean, we're going to be doing, I'm going to set this up as the mean of our difference of proportions. And we just set that up equal to our null value, which is 0. And that comes from where? Where's our null value? Right here. Okay, our standard deviation is a little bit more complicated. Well, I'll give you the formula in a bit for it. But okay, so it's going to be 0.70 times 0.3. This is for Emily's data. It's going to be divided by our first sample size, which is 15. And then for Lakeisha, notice here I'm using the 0.7 for both of them. I'm using that combined probability. I always do that, combined proportion. And if the sample sizes had been different, then those numbers would be different. But they, based off of our fake experiment, they were both 15. I pretended to give half of you one and half of you the other. Okay, so when we solve all of that out, we should be getting 0.167. All right, so our general formula here is we're trying to find our test statistic, and it's going to be equal to our statistic minus the parameter, all divided by the standard deviation of the statistic. All right, so we're going to be plugging this stuff in. Our statistic was 0.2. So specific formula. Oh, I guess I should write out the specific formula. We're trying to find the z-score. So specifically to do that, it's going to be p hat sub 1 minus p hat sub 2. We actually already did that. That's where we got that 0.2 number, and that was the difference in our fake data of how many people, or the proportion of people who called back Emily minus the proportion of people who called back Lakeisha, minus, and then I'm going to do the difference of my population. And this, we're assuming the null value is true. So even though we don't truly know, like, beyond our sample, we're just going to go based off of our null value for that. And then I'm going to divide that by the standard deviation, which we did. I'm just not going to write out the whole equation because we're just going to be plugging that right in there. All right, so showing our specific work, or the work, it's going to be 0.2 minus 0 divided by 0.167 divided by the standard deviation. And when we do that, I'm just going to double check that I'm getting what I want to get here. Yep. 0.2. No. Oh, wait, I typed it in wrong. That will do it. There we go. Yes. Okay. Our z-score here is 1.2. That is our test statistic. It's our z-score, so I can go ahead and put that up there. From here, we need to find our p-value. This is like the whole point of all of this stuff, is to calculate that p-value. So before I do that though, I'm going to make my picture of a normal curve. I'm going to go ahead and erase the work that I have down here first. So hit pause now if you still need to write that down. Okay, so I'm going to draw out my normal curve, label it. The mean is always your null value. I'm going to go ahead and label this. So my mean was 0, standard deviation was 0.167. I do need to be careful here because the large counts condition, remember, that wasn't totally met. And so I'm going to go ahead and pretend this is normal, but we have to be cautious about it. Okay, and so what we're looking for is something that is, we got a difference of 0.2. So we're looking for 0.2 or more extreme. But because our alternative hypothesis was just not equal to, then I'm also interested in this. I'm interested in anything that is as far away from our result as what we got in our fake sample. Okay, So we've done a few problems like this. Hopefully it's getting a little bit more familiar. There's a few ways you can solve this. We can do normal CDF and use as our lower bound negative 0.2 as our upper, positive 0.2 the mean and standard deviation just from here, so 0 and 0.167. When you do all of that, let me do that so I can get our data for that. Negative point, I guess I don't need to say it out loud, I already did. Okay, when I do all of that, I'm getting 0.769. However, be careful, that's not actually our answer. That is this part is 0.769. If I'm trying to get everything else, the part that I actually shaded, I have to do 1 minus that answer, which gives me 0.231. So that's one way you can do it. And to me, that's the easiest way. You can also use your z-scores. If you're going to use z-scores, you can still use normal CDF. My lower bound is going to be negative 1.2 because it's 1.2 standard deviations below the mean. My upper is 1.2 because it's positive 1.2 standard deviations above the mean. And then if you do that, you have to keep your mean at 0 and your standard deviation at 1. That's like, if you're using z-scores, you need to use 0 and 1 for your mean and standard deviation. And then when I do that, I'm still getting this same number. So then you'd still have to subtract it from 1. So either of those are good ways to do it. So our final p-value here is 0.231. All right, last step here is concluding. So there's 2 steps to it. You have to interpret your p-value, and then we have to make a conclusion based off of that. All right, so assuming H sub 0, our null hypothesis, is true, and that would be that the difference between the proportions of callbacks is 0. I should make that look like an equal sign, not a not equals. There we go. There is a 0.231 probability of getting a difference in sample proportions of 0.2 or greater purely by chance. So hopefully you're noticing this is actually a fairly large probability. So that's going to come into our next sentence here. So because 0.231 is greater than our significance level, is greater than 0.05, we fail to reject our null hypothesis. And we do not have convincing evidence of a difference in callback rates based off of name. So, just trying to explain this a little bit more. So because, okay, if we assume there is no difference in callbacks, right, then even if there is no difference, we would still just randomly get a difference of 0.2 or more just by chance 1 out of 4 times, which in statistics is pretty often. If it was something where it would be like super rare, if our p-value was like 1%, what that would mean is that we would only get our results 1% of the time. And then that would count as convincing evidence that actually there is most likely discrimination here happening, because like the chance of this happening if there wasn't discrimination is so low. All right. But that was just based off of our sample. In the original study, researchers sent resumes to commonly white or commonly black names, randomly assigned, to firms in Boston and Chicago. In total, you can see our results here. 246 out of 2,445 commonly white named resumes, and they used Emily and Greg to control for gender, received a callback, and 164 out of the same number commonly black names, and it was Lakeisha and Jamal for that. Maybe they had other names too, but those were like the ones that I read in the article. Named resumes got a callback. So is this evidence more convincing or less convincing? Explain your results. So I want you to ponder that, type out what you can, and then when you're ready to hear my thoughts on it, you can hit play. Hopefully you thought this was more convincing. And let's talk about why. Group sizes were larger, for sure. Anytime we're getting results with more people, like 15 versus 2,000, that's a lot more convincing. Also, without actually making you conduct this whole study, I'm going to tell you that the p-value here, the p-value of getting this result, is 0.00002. That is less than 0.05. Based off of our results, we got something that was pretty common, 0.23. This is much less common than that. So we could go ahead and say that based off of this study, we can conclude that there is discrimination happening because the chance of these results happening is super, super low. So that's that. Let's take some notes. Let's see, most of this we actually already covered. Did we cover all of it? Hang on, let me just go back to my notes for the last part. No, not yet. Okay. I'm going to give you the formula for z-scores. If we're doing a test in difference of proportions. So our z-score formula, we're going to take p hat sub 1 minus p hat sub 2 and subtract p1 minus p2. And we're going to divide it by the standard deviation, but I'm going to give you the whole formula here. Get ready. It's big. And notice in the denominator, I'm going to be using the combined proportions. So divide that by my first sample size, and then it'll be same thing divided by my second sample size. And yeah, everything else that was in my notes for this lesson, we actually already put in our notes for the other part that we just did. All right, cool. So for the check for understanding, go ahead and pause here if you need to. The check for understanding is asking you to do a very similar process to what we just did. Stating, planning, doing, and concluding. So I want to walk you through this, and then when you're ready, I want you to give it a shot, get as far as you can, and then as always, we'll go over it. To study long-term effects of preschool programs for poor children, researchers designed an experiment. They recruited 123 children who had never attended preschool from low-income families in Michigan. Researchers randomly assigned 62 of the children to attend preschool, paid for by the study budget, and the other 61 to serve as a control group who would not go to preschool. One response variable of interest was the need for social services as adults. Over a 10-year period, 38 children in the preschool group and 49 in the control group have needed social services. Do these data provide convincing evidence that preschool reduces the later need for social services like the ones in the study? Justify your answer. So we have to state, just like we did in the activity we just finished, plan, do, and conclude. Get as far as you can with this. This is the first time I'm sort of just letting you do the whole thing on your own without fill in the blanks either. So when you're ready or if you get stuck, you can hit play. For our first step, stating, we have to say what our parameter is. So P1 minus P2, which is the true difference in proportions of children who will need social services. And then I'm going to say the direction. Let's do preschool minus the control. And then in this section also we need to state our hypotheses. Our null hypothesis is that there is no difference. So if I subtract them, I get 0. The alternative hypothesis is going to be based off of this word here, reduces. So we're really looking to see if the preschool kids have less need for social services than the non-preschool kids. So if I am doing preschool minus the control, my alternative hypothesis is that's going to give me a negative number, like because the preschool need for social services is less than what we're subtracting. Okay, also let's do our significance level. Doesn't tell us in the problem, but just going to go with 0.05. And then it's going to be helpful to actually find our combined p-hat. So I'm going to do that right now. So my numerator is going to be all of the preschool kids who needed social services plus all of the non-preschool kids who needed social services. My denominator is going to be my total sample size, which was 123. And that gives me 0.71. We'll need that in a little bit. All right, so that's the state section. Next up, we need to plan. So we have to say what procedure we're doing. It's going to be the 2-sample z-test for P1 minus P2. And then we're going to check conditions. So random, looking back in the problem, yes, the researchers randomly assigned. So I'm going to say random assignment means we can show causation. Okay, we also have to check for 10% condition, but here we don't need it because we're not sampling without replacement. Let's check for large counts. Okay, so let's see, my preschool group was 62 kids. Based off of our combined proportion, I'm going to multiply that by 0.71 to get 44. So what this means is that we would expect 44 of those kids to need social services. And then I'm going to use 0.19 here. That's going to be the proportion of people we would expect to not need social services, and that gives me 18. Both of those are greater than or equal to 10. Cool. Let's do it also for the no preschool kids. So same thing, but here my sample size is 61. When I do that, we're getting 43.3 and 17.7. Both of those are greater than or equal to 10. And so this will tell us that our sampling distribution is approximately normal. All right, I did give myself one blank page here, but not enough. Because the next section is sort of long, the do section. All right, so we have to state our general formula. So it's going to be test statistic is equal to your statistic minus your parameter, all divided by the standard deviation of your statistic. Okay, and then our specific formula, here we're looking for a z-score because it's a z-test. And so my statistic is p hat sub 1 minus p hat sub 2. My parameter is p sub 1 minus p sub 2, all divided by, here we go, this is big, oh boy, p hat sub c times 1 minus that. And that's going to be divided by our first sample size. And then same thing at the top, divided by our second sample size. All right, so when we plug all of this in, our numerator is going to be negative 0.19. And where that comes from is, we didn't actually calculate this yet, the proportion of kids in preschool P hat sub 1 is 38 out of 62, which is 0.61. And then P hat sub 2 was 49 out of 61, which is 0.80. When I subtract these, 0.61 minus 0.80, that's how I'm getting my statistic. The parameter I'm going to use is my null value, which is 0. And then filling all of this stuff in. Let's see. Our combined p hat is 0.71. So I'm just going to work just on the denominator here. So it's going to be 0.71 times 0.19, all divided by my first sample size, which is 62. And then same thing on the top, but this time divided by 61 because that was my sample size for my second sample. When you do all of that, you should be getting 0.082 for the standard deviation of our statistic. All right. When you divide all this out, we get negative 2.32. And I just want to stop right here for a sec. If you're getting a z-score of negative 2.32, that just means it's very far away from the mean. That's 2.3 standard deviations away from the mean. So if you think about a normal curve, that's going to be pretty rare. We still need to actually calculate our p-value, but just because it is that is a fairly large z-score, we're probably going to be getting a pretty small value for our p-value. All right, sketching this out. Let's see, I've got my mean. I'm going to label my mean and my standard deviation. And then I'm just going to solve this the way that I think is easier, but as I've said, there's a couple ways to solve this. We are looking for a difference of negative 0.19 or more of a difference. If we got more of a difference, that would be of note as well. That would also help support our alternative hypothesis. All right, so based off this, it's going to be normal CDF. Our lower is negative big number. Upper is negative 0.19. Our mean is 0. Standard deviation is 0.82. I think I typed something in wrong. Let me check. Oh, yep, 0.082 for a standard deviation. There we go. That looks better. So then for our p-value, hopefully what you're getting also is 0.0102. Okay, so that's it for the do. Just we got to remember this. This is that's why we did all that work, is to get that number. All right, conclude. Assuming h sub 0 is true, our null value, or our null hypothesis, and I'm going to say what that is. That was that p sub 1 minus p sub 2 is equal to 0. There is a 0.0102 probability of getting a difference of sample proportions of negative 0.19 or lower just by chance. So that's the first part, but then we have to make an actual conclusion based off of that. So because 0.0102 is less than 0.05, we reject the null hypothesis. We have convincing evidence that preschool reduces, and I'm using that word here because if you remember earlier, we had random assignment. That means we can show causation. So we can show not just that they're correlated, but that preschool causes a reduction in the later need for social services. And that's a lot. I know. I'm gonna feel free to pause and get that all written down as needed, but this is the end of whatever part we're on. Part 2. Okay, see you soon.